Berkeley has some work to do to clean up those offices and get them all to have AC or do something about that, or even give fans to them, but it's crazy. So anyway, I think we're back past that. I think we're at a good stage now. One of the things we're going to talk about in this class is warehouse scale computing. This is one of the most amazing classes that exists at Berkeley, to go all the way down from current flow to switches to transistors to a machine that runs RISC-V, and then you go up through the hierarchy to be able to build a full machine, to thinking about, wait, what if I had one machine? Could I have multiple machines that have multiple cores in these data centers? We'll actually talk about that. So this is news about data centers, because that's in our scope now. Texas regulators, by the way, you might know data centers consume a ton of power, and Texas regulators actually want the data centers themselves to serve their own power. They're like, look, bring your data centers to Texas, but you can't be tapping onto our power grid and making it work. You got to bring your own power. So this is new regulation that the Texas legislators want to do, to say, if you want to build a new data center, you have to bring your own power plant too, which is fascinating. A power plant aside, I mean, maybe that's great, but it's very efficient. There's a lot of loss to take power from one place to the other. So it's actually really efficient if you're going to have it used here to have the power plant right next to it. So actually there's some efficiency gains that it should be had, but you might imagine some solar on the roof, maybe a mini nuclear thing that's very safe. But who knows what they do to bring power into a system? You know, they use a ton of power. I can't imagine all the wind turbine and then solar. It's still not enough for what the data center needs. So maybe right by a river and there's some hydro. Who knows what they're going to do? But they've talked about mini nuclear reactors, and that might be the future. It's very interesting. All right, let's get started. Ladies and gentlemen, welcome to C61C, a new lecture on a new topic called RISC-V Datapath Part 1. Woo! Good to see you all as always. For anybody watching on Zoom, if you ever wondered, like, I'm not coming to class because there's not enough seats, there are hundreds of open seats. Come on and join us. It's a lot of fun attending lecture live. This is a new topic. We finished the SDS topic. That was 4 nice lectures, taking you from what SDS is to combinational logic to state diagrams to blocks. Now we have big blocks. Today's lecture is plugging those blocks together to start to build a very simple CPU. So Datapath is one part of that. I'll talk about it in a second. So here's our topic for today. Number 1, let's build a RISC-V processor. Number 2, let's talk about the CPU elements and maybe thinking about stages of what the CPU is doing. And that stages really helps our building process. We're going to just start add and sub. So today is just unbeatable. Can we build a machine that actually literally runs add and sub? That's amazing already. To go from nothing to building a machine based on 4 lectures, and today to handle add and sub. And then maybe we'll even think about add-I at the end. It's pretty cool. So it's going to be a good lecture. All right. Again, this is a new topic. If you didn't know SDS, you actually can just treat them as black boxes. So if you were still behind on your lectures, come on, re-engage. Treat everything I show you. If you don't understand how it's built below the scenes, just treat it as a black box that you'll use in a high-level spec. We're here, obviously, the lower side of this, the hardware side of the hardware-software abstraction layers. We've seen that before. We're coming up from the bottom. This is thinking about the old school 61C and how we come up. If you remember seeing this picture, you might have said, oh, data path and control. I don't know what that is. Today, you're going to know what those are. But you know, in theory, all the things up through that. So it's pretty cool that you're biting to this general ISA from the bottom, and you know, in theory, all the things. We didn't really talk about fabrication, but assume that somebody magically fabricates these chips that makes it work. Okay. This is where it fits into the new school 61C. We're still at the lowest level of logic gates. These are going to be put together to be functional blocks. That was actually last lecture. Hey, a functional block called an ALU, a functional block called a MUX. All these things we're going to be using today. And in general, hardware descriptions are parallel all the time, and you can't turn them off. The MUX is like, hey, there's an and, there's an or, and one of those guys is going to drive the output. The other one is still doing its work in parallel. It's really a lot of parallelism. There's 32 parallels of things happening here, and there's another block doing another 32 things in parallel, and then one of those ends up driving the output. So all that parallelism is still there. It's pretty exciting. You've seen this picture before where I showed you the block on the left, which is a processor, and the block on the right, which is memory. We're focusing on the processor for today. We're going to assume memory is a black box. We're going to treat that as a black box for today. And there are 2 parts of this that I'm finally explaining. Part number 1 is called the data path. This is the active wires that you decide to put together. That is to say, Look, I've got water. Imagine an aqueduct back in the Greek days. I got water coming in. How do we have this flow to each of the houses? How do you split it? How do you come in? Well, they're not going to be there. They're on vacation. How do you turn that water off so the water doesn't go to that house when they're on vacation and flow to other houses? That's basically what we're doing. It's figuring out where the data comes from and goes to. So we're going to figure out what the boxes we need and then how to flow them that way. And then you imagine in the water analogy, every spigot, every path has a handle. If you take a shower this morning, there's a handle turning the water off and on. That's what control is. Control is the brains, maybe implemented with an FSM you just learned about, that turns the spigots on and off to tell you, today I'm driving the register, tomorrow I'm going to be driving the memory. Whatever that data needs to flow, those spigots get turned off and on by the control. So the control is the brain, if you will, the marionette, and the data path is all the wires you build to handle all the possible cases for data going from one place to the other. It's super cool. Okay, any questions about control and data path and this picture? So we're looking at the left picture of the CPU. Control is the guy above, which receives, it's not just blind, it receives data from the data path and sends information to the data path. So it actually, based on some decisions, you might think about a branch if equal. Well, some boxes got to compute whether that branch is equal or not, the two registers are equal or not. So that data comes into the control. The control says, okay, now that I have that decision, I'm going to now control a mux, whether the PC gets PC plus 4, which means you don't take the branch, or PC plus the immediate, which means you do. See, so all that. So the control takes it in, makes a decision, and then drives the choice of a mux of who gets to drive the next PC. That's an example. We'll see branch equal next lecture, but today we're just going to do add, sub, and add I. So this is the reference card. If you have the book, if you bought the book, how many people bought the book? Let's get ahead. Let's do some active learning. Bought the book. Okay, good for you. Great stuff. Support our authors, one of whom is a faculty member at Cal. This book is an amazing reference. It's really great to have. It's one of the only books that I guess is supported by the Berkeley faculty. This is the official Berkeley 61C book. There are others that are out there in the same space to teach RISC-V or to teach machine structures, but this is far and beyond the best-selling book, by the way, if you didn't know this, but it's far and beyond the best-selling machine structures book and architecture book for introductory students in the world, actually. So here's the RISC-V reference card. There's a green sheet on the front of that book, this shown in white, which essentially shows here's your ISA, here's your RISC-V ISA, and here's effectively what are the registers being read to and read from. This is an actual piece of hardware that implements RISC-V. It's pretty cool. High5 is a company that puts this out, and so that's an actual machine that executes all the RISC-V instructions, RISC-V instructions. Pretty cool. All right, let's talk about building the CPU. We're talking about Datapath today. For 2 lectures, Datapath, and 1 lecture on Monday is control. So control, we're going to see, is a lot of complication there. Datapath is pretty easy, relative to control. All right, so today we think of all the combinational logic subcircuits as block diagrams. For example, last time I showed you a 1-bit wide 2-to-1 mux. There's 2 knobs on muxes, how wide each channel is, and how many different lanes come in. This is 1 and 1. Each lane is 1 bit, and I only have 2-to-1 mux. In general, we're going to really like this. We might have a 3-to-1 or 4-to-1 mux, we'll see. But for now, think of this as a black box. It's just going to draw that as a big block, as a black box, 2 32-bit inputs, A and B, and there's 1 32-bit output, and there's a single bit S controlling that. So that's how we're thinking about it today. We also showed that last time. We talked about an N-bit adder. Here we're just going to draw it as a black box. As an adder takes 2 32-bit inputs, A and B, has a carry in, which is over here, the C0, and has a carry out, as you saw there. So again, this is just a black box we're going to be using. Finally, we saw a very simple ALU, arithmetic logic unit. It means sometimes it's doing arithmetic stuff like adds and subs. Sometimes it's doing logic like ands and ors. We're going to think about that as a black box ALU diagram. So if you see this, you know we mean the guy above. So when you see this, we mean this. That's how we build that, okay? So that's what it's called. I'm connecting last lecture to this lecture. But from this point on, we're talking about that black box called ALU. Below it is the ALU operation. That's the kind of signal line that tells you what to do. Are you doing an and, an or, an add, a sub, etc.? And there's going to be 1 32-bit result outside of that, okay? So far, any questions on that? Just connecting last lecture to this lecture. All right. Here's the big idea. I try to tell you every lecture, what's the big idea? The big idea, this is really big, is that one instruction per cycle. This is super cool. This is a very simplified model. We'll get more complicated today, but we're keeping it simple for today. We're going to have one, for every clock cycle, we're going to finish one instruction. But Dan, you told me that going to memory is 500 clock cycles. Pretend you didn't know that. Pretend that somehow I magically make that work, that we're going to slow the clock down so that the time to go to memory and come back, just for now, we can get that, make it happen, okay? So every instruction, whether it's load word, store word, or with just a simple add, we can do in one clock cycle. That's the big idea today. We're going to try to create wiring diagram to make 3 instructions, add, sub, and add I, work with 1 instruction per clock cycle. You know, the 2 things we have at our disposal are combinational logic elements and state elements. State elements store data and remember it between clock cycles. Combinational logic elements do not. They're just simple, pure functions. So here's the picture. And you know, based on pipelining we saw a wonderful diagram Perrin showed, you can build a small little circuit to count, I think it was like 3 ones in a row. You can already build that. We're going to basically do that same idea, but for larger structures. So here's our clock, which drives our state elements. You can tell it's a state element because magically I draw a little triangle at the bottom of each element. That means these are state elements. That means there's a clock that goes into that. If there's no triangle, it's a combinational logic element, okay? All the guys on the right are just a combinational logic to make it work. And here we go. This stores our state. Then there's an output into combinational logic that decides something. It might decide our next state. It might decide what the next value that needs to be in some of the muxes are. All the combinational logic somehow magically works. All the blocks I showed you before were all CL elements. This was a mux. That's a CL element. This was I think an adder. Let's go back 2 slides here. What do I have here? These are all CL elements. Nothing here has a triangle going to it. These are all combinational logic elements we're going to use in our system. Okay, so data comes in from our state elements. Remember, the value of these state elements is they hold their values solid until the rising edge of the clock, and then they turn around, and if they're told, hey, load, then they might load some new values, but they're holding it stable. Then the combinational logic does its work, and that takes a while to stabilize, and we're slowing our clock down so it's all stabilized well in advance of T sub what? T sub, remember this word? T sub loud? I heard it. Setup. T setup. T setup is the time before the next rising edge of the clock. It's like if you get up at 9, you better kind of have your alarm go off before 9. It's like it's a time before rising edge, and the values better be stable for all the flip-flops that are locally inside each of the state elements. Not every state element has flip-flops, but all the state elements have a T setup, and so there's a time that says you got to stabilize before that. So the combinational logic does it. It has its adder delay and a shifter delay and all that, and a mux delay, all these delays, and then they're stable. And they're stable before setup, for setup time before the next rising edge, and the whole thing repeats. And every time a new clock hits, it's a new instruction. It's pretty cool. It's really very exciting. Okay? So current outputs of the state elements drive the inputs to CL. We call it combinational logic, or CL, whose outputs settle at the inputs to the state elements before the next rising edge, and I just mentioned that, before T setup, before the rising edge. And there's our feedback that feeds those values back in there. And so I'm slowing the clock down so it all works, okay? So, and by the way, who's ever overclocked their system? Who's ever like bought a CPU, a faster clock chip, and had this is a big deal back in the day. I see one hand, anybody else? 2, 3, 4 in the back, okay? If you continue to turn the knob of your clock up, what happens? It's too hot, A. It's also unstable. Like the values are wrong. Your hard drive doesn't store the right value. I did it myself. I literally, back in the day, had a Mac, and I sent mail to the guy, and I wrote him a check, and he gave me like 4 different clocks to try. And I tried that one, it was faster. I tried that one faster. I tried this one, and it worked, but then all the files were corrupted. No, like I wrote a Photoshop file. It was like, what? It's so cool, the blur. And then the file, I couldn't load it the next time. Like it was corrupted. Why is it corrupted? Because I violated the T setup. T setup has to stabilize. Those values have to be stable. If you turn the clock too small, That delay through the combinational logic violates T setup, and then it doesn't write to a flip-flop, and flip-flops might go into a weird state. Who knows what happens? But that's what was happening. Now you know why. When you turn the clock speed up too much, what's breaking? It's T setup gets violated, and the flip-flops don't become stable. Isn't that pretty cool? All right. At the next rising edge, so here's the key. I've got a new value in cyan, and then the next rising edge, those values get loaded in. If anyone's that need to be loaded, PC is going to change every time, unless somehow you're jumping to the same instruction, which might be a loop. All the memory, if you're loading the memory, if you're storing memory, that instruction memory, there's actually no new data for that one. If you're storing this in memory, that's when it gets stored. On the next rising edge, it gets stored. So it gets stored on the end of it. So it's like, okay, stored in memory, stored in memory, stored in memory. Wait. Rising edge, now you're putting the store in, and you got the data. The data only stores at the end of it, like at the end of that time. Here's the window of when that clock was, it goes up, it goes, okay, now it's, okay, today's a store, okay, store, it goes down, and then it goes over again, and then the value to be stored is waiting at the front of that memory, and then the next rising edge, that's when it gets stored. It's kind of cool. It gets stored at the end of the day, if you will. Question?
Delay, is it pretty stable, or does it have some randomness?
No, the combinational logic delay is not random. It is declared as part of the system. They say, it's like you go to Fry's and here's the specs on it. So you know that, and then you can build, in advance, you can say the clock can be no faster than this based on the critical path for all the CL that I have. It's not like a random value. It is some value. Now, it could be that if the value doesn't change, I'm stable way before my spec. But it's the spec is, here's the longest I'll ever take to be stable to do some add or some shifting or some that. Okay, good question. All right, pretty cool stuff. All right, so here it comes through, and then it logs through, and this is the animation for that. All right, so what are the state elements we need? This is a big picture. What are the state elements we need? Let's go to Radio Shack. Let's go to Fry's. Let's go to your favorite electronics store. What do we need to make this happen? We're trying to make this guy on the right happen. We need at least these 4 things on the left. Let's talk about them for a second. Number 1, we need a register, the 33rd register, our program counter. It's a single 32-bit wide register which stores what instruction am I running today. We know that before. We've seen it before. That's it. It's standalone. We need a register file, which is 32 bits wide and 32 rows deep of all the 32 registers I have. The only thing that's a special case is 0 never changes. It's always 0. We also are going to need memory, and that's the guy on the right. And here's the big deal, and here's like the kind of lie I'm going to tell you. We're going to treat these as 2 memories. Later, when we talk about caches, you'll see why they're 2 memories. We're going to treat them as 2 different things. Why? Well, in one instruction cycle, I need to read memory down in the code area to figure out what my instruction is. This PC points to, this program counter points to some place down here in the bottom, which is the instruction. Oh, it's an add today, it's a sub today, it's an add-I today. That tells me what 32 bits I'm doing today. So I need to be able to read from memory every instruction. Wait, what? Yes. You're going to Sacramento every instruction to just, you knew this already, to read what I'm doing today. Oh, it's an add. Tomorrow it's a branch, right? Every line has to read from memory to figure out what it is, okay? That's why we have caches. We'll talk about that later. But somehow it's useful to think of this as IMEM for the instruction part of memory, which is down here in the lower part, as read only. I'm just reading that. I'm never writing to my code. I'm just reading from that. And DMEM, which is the normal memory you think about, data memory. So if I'm load word or store word, load byte, store half word, load half word, that's DMEM, the data part of it. So I stands for instructions, D stands for data. These will have 2 of them because I need to have them when I put them together. And we're going to see that they actually are separate because I have these caches that are going to be local copies. But don't worry about what the caches are. But just for now, we think about it as 2 different blocks. Even though there's really one big block on the right, I'm thinking about those 2 blocks in functionally. Okay, it's useful to use. Anvi, question.
The next line after the setup time or after the combination?
Good question. PC. When does the PC change? Just like the slide before, the PC has the current instruction. It's an add, and let's say the one below it is a branch. Okay, so PC plus 4 is calculated and sitting on the input line to that register. And so so it goes up, it's all add. It's the same PC. It's holding locked at that address of the add. It goes up, it goes across, it goes down, it's still add, still the same value. At some point, some logic says PC plus 4. The control says, oh, I'm not doing a branch, so it is PC plus 4. So PC plus 4 is sitting in the back of that register. And when it rises, then it goes loads, and it'll be plus 4. Because the next one after an add is going to be whatever the next instruction is, which here is a branch. Okay. Now, if it's a branch, then the branch could be, the input could be what, PC plus 4 again if you don't take the branch, or PC plus some huge immediate if you do. So that gets calculated by the control and by the data path. We haven't talked about how that gets worked. And then on the back of that PC after the branch is the next one, which is, do I take the plus 4? Do I not take the branch plus 4? Or do I take the branch plus immediate? And that's waiting. And so all of a sudden the control knows which one drives it. And then whatever happens, the rising edge after the branch is the next place to go. It's so magical. It's really cool. And we slow the clock down. It happens all in one clock cycle. That's the key. Okay? All right, did this. Joey CPS, blah. I think I said this. Every single, so here's the key thing. I think I might have said this before, but this is really critical. Every instruction's job, unless it's a no-op, which means don't do anything, is to change exactly one state element. Like go back, like literally go back to the slide of all the RISC-V instructions. Every single one is to change one state element. Add's job to change the destination register. Branch's job to change the PC. What else? Load word to change a register. Read from that, but change a register. Store word to change the memory. Like every single one we know changes one of those state elements. Isn't that kind of cool? So everyone, like, wait, one of these guys on the left gets affected by every instruction. It's really quite cool. And sometimes in clever ways, two of them get affected. You change your PC and your store register. Like JAL-R. You just up to the register and you change your PC. That's pretty cool. So sometimes two of them. That's kind of neat, right? All right. Okay. So this program counter, we can draw as a black box as this picture right here. It's a simple register. It's got data in, which is the next PC. Data out's the current PC. And write enable says, and by the way, all registers, it's useful to have write enable to say, do you want to write when that rising edge goes up? When write enable is asserted or 1, it says, do you accept the inputs on your back and spit them out the next clock cycle? So it's useful to have a write enable there. Now, I just told you that every instruction, we're going to be running this every time. So that's going to be always on for the PC register, okay? So inputs and inputs bus write enable tells you the control on asserted is 1 or high. When you want to change that, again, you're always reading the new guy. And sometimes the new guy happens to be this. If you somehow jump to yourself, then it's the same value, but you're always reading the new value. Outputs, again, is the inputs of output. We often see this as this picture in a logical diagram in Logisim as this. So now you look at these two pictures. D and Q. D, data. Q stands for quiescence. It means like stabilizes, like data, and like the stable version of it out. It's called the quiescent version. WE stands for write enable, and the little triangle is my clock. Pretty cool. So one 32-bit register, literally, there's 32 bits. And that's it. And they get loaded every single clock cycle. That's all it does. Any questions about the PC? We're going to try to build this together. Next, bloop, behavior. If write enable is 1 on the rising edge, set data out equals data in. You saw that before. That's all. Paver and I talked about that last week. Okay. All other times, data out doesn't change. Super useful to just have it locked in as the PC. Whenever any other time other than the rising edge, I'm holding these values. The current PC is stable for anybody who needs it in the future. Like the +4 box, it's going to be adding that and giving it back to me. Okay, next, this is a little bit more complicated. The register file. Whoa, what's going on here? This has a lot of ports. This is kind of cool. You start looking at this as a black box. What's the spec of this? It's a black box. You think of it, what do I need to do for this register file? And what's really cool is you need to actually ask your ISA, tell me ISA, you go through every single instruction saying, what are you ever going to ask of my register file? ISA says, you know, guess what? The add and the sub and all the R type are going to read from 2 guys and write to 1 in 1 clock cycle, right? Read from RS1, RS2, write to RD. So this better have, let's look at let's see if it makes sense what it has, what all the ports. I'll go through here. You better have 5 bits each for how you specify RS1 and RS2 to read from. You better have the data that I read. This is like R of RS1. You think of this as an array, it's like the R, the capital R, open square bracket of RS1. This is R of RS2. So those two 5-bit channels tell you what data 1 and data 2 come out. All memory and register file, I think I say this here. On a read, act as combinational logic. You specify 5 inputs, some combinational logic magic happens, and there's an output. It's kind of cool. So there's no clock involved on a read. There is a clock. Why? Because I also need to write. I need to write to RD sometimes. So I also need 5 more bits to tell you what the register write is. Here, rather than RD, we call it RSW. That's like the label on the box I bought from Fry's. We call RSW. And I take the RD bits and I pass them into RSW. I also need to tell it what the 32 bits I am writing to it. That's data W. That's it. I've got a reg write enable, which means on this instruction, am I changing the register or not? What instruction am I changing the register? Almost all of them. Which one am I not? Store word. The job is to change memory. Or tree, branches. I just change the PC. I don't change this guy. Okay, so branches, I don't change the register file. And store word, store X, I don't change the register file. And so here, look at this example. R of RS1. RS1 selects it. It's like an array. Like it's the index. It's like a 5-bit index up to the 32 possible rows. And it grabs the value and stuffs it on data 1 and data 2. Here's the key. The clock input, I say this here already, the clock input is only a factor on the right. And is there a delay? There certainly is a delay. If I want to read from that value, here's 5 new bits for RS1. After some combinational logic delay, that data is available on data 1. So there is a delay in the read process, but there's no clock involved. It's kind of cool. Question in the front. Yeah. Alex.
You ever read without the value that you just read? Because otherwise, how would you know?
Do I ever read without storing? What do you think? I never read without storing? What's a branch do? Branch says, here's 2 registers. Read them, change the PC maybe to be +4 or plus immediate. So reads, no writes. So sometimes you have needs with no writes. Okay, cool stuff. I think I said everything. Any other questions about the register file? But it's kind of cool. It makes sense. Anvi. Data W? Yeah, sure. If I'm going to be writing to this register file, I need to say, like RD, it's the 5 bits to specify which guy gets an add. 5 bits specify which register row gets updated with the sum of R of RS1 and R of RS2. So I need to be able to, but here is the 5 bits of who gets changed, and here's what I'm changing it to. So I need data W to specify who gets in there. And that only has effect if reg write enable goes high and the clock goes high. That's the only time I need it. I need that time. Okay. And by the way, there's T setup for this. All those values better be stable. Well, not all the values. The only values I need stable are RSW and data W need to be stable before T setup, before the rising edge of the clock. The rest of the guys can be changing all they want to. RS1, RS2, they can be changing while the rising edge happens because they're not used in the write. For a write, I only care that where you're writing to and what you're writing are stable long before the rising edge, and that's T setup before the rising edge. Good question. All right, so far so good. Bloop. What does it say in the bottom? I think I said this. For all reads, it behaves like a combinational logic element. Just kind of circle that thing for yourself. I said that already. All right. Now memory, and I told you kind of the secret thing that we're going to treat this as 2 different guys, as an IMEM and as a data mem, okay? So here we go. Let's think of this. This is, here's IMEM data mem. This is the normal, I'm showing you here, if I have data W, then that must mean I'm talking about data mem because I'm going to be, I'm only reading from IMEM. IMEM, I'm just going to be reading from this. Data I'm going to be writing to. So here we go. Here's memory. This is data mem, DMEM. For this class, 32-bit byte address memory space and memory access with 32-bit words. We talked about that before. So this is the 32 bits of the address I'm using. If I'm reading from that, like a load word, that's the data. Read is what what's in that memory location. That's mem of address. Data W says, if I'm writing, this is the address, and that's the value I'm writing to. So data is the data, and address is always the address, okay, in general. I have mem read write. Am I reading or writing to that box at that particular time? I've got a clock as well. Okay. Like a reg file, this is almost identical to the register file, which is if I'm writing to it, then address and data W better be stable before T setup. We said that already. And if I'm not writing to it, it just always, whatever value happens to be on ADDR address, it goes and finds what's at that memory location. Isn't that fascinating? One of the things that blew my mind when I first learned this material is like if I do an add doesn't touch memory, right? Add just register touches register. Hopefully you all know that by now. But the wires are still wired through our data path we're building today into the memory file, which means the memory goes, oh, you're looking at this, and it's doing its work to go find the value. And on the output of data R is whatever that value is. But you're never using it because an add is only modifying the register file. But it's still working. Remember, you can't turn hardware off, people. This thing is still working like I'm doing combination logic, doing my thing here. Fascinating, right? So, any questions about the memory box? As I said here, if memRW is 0, mem behaves like a combination logic block. Meaning like on an add, turn it to 0. Better not be changing the memory file on an add. But it's still doing its work. It's still figuring out what you wanted at that particular set of 32 bits of an address. Still looking at it. Okay? Good. All right. Now, I'm going to divide these into two different guys. One is called IMEM for the instructions. One's called DMEM. The cool thing about IMEM is I'm just reading. I'm just reading from the code area. So guess what I get to do? I remove the clock from it. It's literally just, I put an address, and here's the instruction. It's really quite nice. I treat it like a pure combinational logic element. It's just reading from that code area, that low part of memory. If you can't see me on video, I'm reaching the bottom. Low part of, okay, here's an add, here's a sub, here's a branch. It's reading from that area. I separate them. I have two separate blocks. IMEM is a read-only block. DMEM is a read-write for load and store word, etc. Okay? Any questions? Cool. So I think I said all this. I think I said all this. I said all this. I said everything here. Okay? Okay. So now, here's what we want to build. We're going to divide this in phases. If we didn't do phases, it would be so hard to have a list of all the instructions on the one side of the board and just try to build it all at once. Building it in phases is the most pedagogically right way to do it, as well as logically the best way to do it. We're going to be starting first. What's the simplest operation? Let's build a data path for that and get it working. Then slowly add the next one and the next one. So we're going to be continually, just pedagogically, which is the same thing they did design-wise, go through and add an instruction and say, how do I have to change it for that and change it for that? And you try to make the minimal changes to be able to support every instruction you want to have, okay? So we break the process into stages, and we think about not only the stages. So it's the stages of what are happening in this one clock cycle. Rising edge happens. 5 different things, 5 different quote unquote stages happen, and that's actually really useful to think of those stages to drive our data path decisions and control decisions. That's our 5 stages, which we're going to go for the next 3 lectures. Just focus on these 5 stages. Just circle this. This is that's like the second big idea. One big idea happens in one clock cycle. Second big idea is 5 stages to it. PC, you read from the register that holds the PC, you say, what's the thing we're doing today? Like, they woke you up. The chickens, roosters woke you up. Oh, it's what PC gets a new value. This is the new instruction. I've never pointed to that before. This is where I'm reading from. IMEM says, let's go to instruction memory and go read that instruction. I don't even know it's an add yet. All I know that there's an address that points to the add, but I didn't know it's an add yet. I go to IMEM, a combinational logic circuit, and I read, oh, it's an add. It's the 32 bits that encode an add. You know what those bits are. You can do it yourself on an exam. I've got to read those registers now. I've got to now do the calculation. I've got to do the add itself. I've got to then work, and do I affect memory or not with that, okay? So these first 2 blocks, we're actually going to call, they're going to call this all one, these 2 blocks, we're going to call this first stage. We still call it the first stage. We call that instruction fetch. So this is not 5 stages in this picture. It is, stage 1 is instruction fetch. These are the 5 blocks. These are the 5 stages. IF includes the PC and IMEM. What do I do? Fetch it. So those 2 count for, it's an add. The next one is decode. I need to be reading the registers. And I need to be doing my control work. Control finally knows it's an add. Oh, it's an add. Okay, quick, look up the table. What do? Add makes that mux do that. Remember the control turns the faucets? Okay, that mux does that. That mux does that. That's when it's doing its work. So in this instruction decode, I'm reading the registers and I'm deciding what the control should do. Step 3 is the execute phase, which is I actually do it. I don't like the word execute because it means kill and something. But anyway, do the thing. Do the thing you're supposed to do. Okay. Do your arithmetic logic. Your ALU, do its stuff. That's what that means. 4th stage is memory access. Do I have a store word or load word? That's what happens in 4th stage. If I have an add, I don't do anything. I actually go to sleep that stage, which is okay. The 5th stage is, look, there's a gap. The 5th stage is anything that came out of that memory has to then be fed back into the register. That's called the write back stage. So that factors in the T setup. If I factor that T setup, then I cover it. Then I go, oh, just add those times up, and that's what I can do. So T setup gets factored into that write back stage. Okay, that's it. So write back anything that has to get written back to the. So here's what's funny: this ALU value, if it's an add, kind of goes around DMEM into stage 5. It kind of skips it, doesn't go through DMEM. It goes around DMEM. It's like there's a stalled truck. You just drive around the truck, and that data goes back to stage 5, which then eventually gets routed back into the register file. Okay. Any questions about the 5 stages? We're going to see this for 3 straight lectures, so you'll see more of this. Okay? Oh, in the back. Yeah, go ahead. Be loud. Tell me your name and to be loud. Forrest, go. Stage 5 includes T setup, but yes, stage 5 includes I got to be writing there. And so if I'm adding these times up for a critical path, I'm going to include the T setup into stage 5. Yep. Good question. Whoop, and there it is. Look, data goes back and it gets fed into registers. It might also get fed into PC. One of these guys actually is take the PC and add it to the immediate and then stuff it back into the PC. So what you got to make sure, but sometimes the value actually gets passed back into the PC as well. Okay, we'll see that. And the clock drives all the clock elements. Notice that IMEM has no clock input, though, and ALU has no clock input. Those two are just CL units, C combinational logic. We only drive the clock on the PC register file and DMEM. All right. Let's get in. Here we go. Single cycle processor. That's the big idea today. Single cycle CPU. Single cycle processor means in one clock cycle, we do every single instruction. Slow the clock down to make it all work. Let's do it. The control logic tells all these boxes what they need to do. So control logic is super complicated, which we'll do in 2 more lectures. Everybody needs to be told what to do. DMEM, are you writing to memory or not? ALU, what's your operation? Register, are you writing or not? IMEM, not sure what you need to tell IMEM. PC, are you loading or not? Okay, everybody gets to tell something. And by the way, IMEM, remember that 32 bits of the instruction, those 32 bits, some of them are the func fields, which tells you what to do. So that data has to flow from IMEM into the control logic, okay? And by the way, it might be useful, maybe like the branch comparator might live over here. So here, I need to know whether the branches were equal. So that's also data from maybe a branch comparator if they're equal down there passing to my control logic, okay? All right, let's do it. Finally, enough setup. Give me the data path for add. Let's do it. This is so cool. We have to build one instruction. Today's job is to literally build a piece of hardware using the blocks that we know about to support add. Let's do it. Here are our bits for an add. Nothing new here. This is all review. This is what's called RTL, often known as register transfer language. How do registers or memory get updated with that instruction? So that add has these semantics. These are things that get changed in the state elements that I have. I told you every state element gets changed by every instruction. Right there, 2 state elements get changed. The register file gets updated and the PC gets updated. That's it. So let's draw the simplest black box that we need. What are the blocks? We need a PC. We need an IMEM to load. I learned it was an add. I need a register file. I need an adder. I don't need any memory for now. So let's not even draw it. Don't even go to first. Oh, you brought the memory. Thank you so much. I'll use it later. We don't worry about it today. So here we go. PC plus 4 happens this way. The PC comes out of the PC. It goes into a dedicated adder. Plus 4 is always hardwired to one side of that 32 bits. That adder then calculates PC plus 4, and that's waiting at the input of the next instruction. So if all I need to do is add, that's always going to go add, and then another add, and then another add, and then another add, because all I know how to do is add right now. All of the bits of the instruction get passed into, remember these fields? Look at the fields on the top. Those fields, literally, look at this. You can now you finally realize why we cared about it. 15 to 19 is RS1. So 15 to 19 gets passed into RS for R1. What's that? RS2, 24 to 20. So 24 to 20 go into RS2. See how now you kind of see like, oh, now I care about where those lines. Now you're finally realizing, wait, Dan, thank you so much for trying to keep the registers in the same place, because I can literally just grab those bits from that instruction and hardwire them into RSR1 or RSR2 or RSW, which is RD over there. RD bits get fed into that. Now I have two outputs of that memory register file, combination logic. I read from the, now this is R of RS1, R of RS2. And look, R of RS1, and I got to add them, pass it to an adder, and the value has to go back into data W. So well, you probably could have drawn this yourself. If I had not told you the answer, you could have done this. But that's it. That's all you need for the add. Let's pause here. That's so cool. Before I go to here, increment PC to the next guy. Oh, by the way, now there's a nice animation we added to show you where the data flows when it goes hot. Split instruction into the index in the register file, so those bits literally get wired differently. Oh, those bits get pulled right from this line. I pull those bits and line those five, indicating the addresses of those three registers affected by this. Feed the read register values into the adder and write the adders back in stage 5. Boop. So here we go. Wake up. Oh, it's PC goes into IMEM. It says, what is it? Oh, it's an add. How convenient, because I only have that so far. Okay, quick, send those 15 bits into the register file. I use 10 of them to read R of RS1 and R of RS2. Here's the data for R of RS1 and R of RS2. What are they going to in an adder? The adder does its work. Plus, it gets here and it gets set up and it's waiting on data W, waiting for the next rising edge of the clock cycle, and then it writes it at the end. Isn't that cool? So it's all waiting, and by the time by the time the next time for the next day, that data gets written and stored in that register, and that's so cool. In case the next instruction had to read from those registers you just wrote to, you got to be ready. So it writes it fast enough to be able to read it for the next guy. So if every here's add of what's an example? A0 gets T0 plus T1. If the next guy you read from A0, it better be there. So that's how it works. So cool. Okay, control logic we only need so far is register write enable, and we turn it to 1, because we are definitely writing to a register at the end of the day. If that happens to be 0, your add had no effect, and that's the wrong thing. You got to obviously change it. Nothing else has a triangle. Nothing else has a triangle with the clock, and so that's the only thing that needs to know whether actually the PC does as well. PC's loading it, but I don't need to tell the PC thing. It's loading all the time. I hard-coded register write on this PC to be 1. It's asserted all the time. It's always loading the next guy. So I don't need to tell it anything. Okay? Any questions about add? We did it. We did add. Let's give it a golf clap. Golf clap for add. It's pretty cool. Golf clap. Golf clap. That's pretty cool, right? I love this. And I tried to go slow enough. I mean, these slides are done. All of us helped contribute to the set of slides that were there. Probably about 20 instructors all contribute to make this really clear. The simplest case, the simplest instruction. The first one you learned was add. First thing you learned as a first grader was add. Let's try to make add happen on an actual piece of hardware. That's it. We built it. And every block here you could build. Wait, what? Yeah, you could build every block here. What do you mean? We built an adder last lecture. We built a memory. You didn't really build memory yet, but you can imagine combinational logic kind of working it out. That you can build memory out of combinational logic. You can build a register file out of combinational logic. It's pretty cool. All right. So for now, memory doesn't exist. So for now, memory doesn't exist. We'll see it later in the next lecture. Let's do sub. No, is that question? Yeah, sorry, I missed the hand. Yeah, go back. Thank you for that. Go.
Quick question.
Sure.
IMEM takes a while to go to memory, so in the register writing to the other register, that happens much faster than going out to get the memory. So it's
Correct. It is the case that I did say that mem accesses 500 cycles normally, but we're turning our clock speed down to allow enough time to go to Sacramento, get IMEM, and have that value out there to be passed to the register file, to be passed to the adder, all those delays compounding, to be then set up for the stage 5 for that, all within 1 clock cycle. So we're turning our way down. That whole 500 cycles to go to memory, it's 1 cycle. So we're gonna be able to read memory in 1 cycle. Okay? We're going to see later there's something called a cache, which makes it actually possible to read in one cycle. But for now, just same thing. I turn it way down. So I go to Sacramento, go there, come back, all in one clock cycle. It just works. Magically, it works. Okay, good question. All right, let's keep going. Let's do sub. How hard is it to change sub? You can already guess what I need to change in sub. Look at this picture. What do you need to change for sub? Yeah, add needs to be changed to sub. Everything else is the same. Add needs to change to sub, which means I got to somehow do what? Take a control line and pass it to this ALU and make it so not just always add, but add or sub. Just one bit of add or sub. That's all I got to do. Let's do it. Okay, same. Now, oh, what bit would I use? Turns out that the two instructions, add and sub, differ in one bit. They're literally the same. By intention. You know what a really bad ISA design would be? Add and sub are totally different. Registers different places. That'd be crazy. No, the smart design would be keep them the same and use one bit. And that literally that 30th bit, 31st bit on the left, 30th bit one in, is your do you do an add or sub today? That's all I do. I take that wire. It's so cool. That goes into the control logic. Control logic looks at that wire and says, hey, I guess I'm doing a sub today. It passes that back into that. So I don't directly wire it from IMEM. I don't take the wire from IMEM into that. IMEM goes into here. It decides, yes, I'm doing a sub, and it goes to the ALU. So what am I doing? What am I adding here? I got to tell it sub, and this is the key part. I'm going to pass in all 32 bits in case I need to use them in the future. Just pass them all in. But for now, I only use that 30th bit, that second from the left. And I look at that and I say, hey, are you a 0 or 1? To determine whether that is an add or a sub. It's literally that. When it's a 0, it's an add. When it's a 1, it's a sub. That's all I'm doing. And you remember that 1 goes into my magical, the extremely clever adder subber? Same thing. Yeah, that's that 1. I literally take that 1 from there to there. It's so cool. That's it. That's the only thing that changes. Any questions? Because it gets harder. We got 5 minutes now to handle the I. I is a lot harder. Add is going to be tough. Okay. Analogy, space mission. The analogy of this, by the way, this is kind of cool, is like this powerful data path is like the International Space Station. And mission control, they call it control for a reason. It's like mission control has the same name as control. You're down at Houston sending signals up to this powerful magical box in the sky. That's what it is. Datapath is the beautiful box in the sky, and mission control is saying, okay, do an add, do a sub, turn your thrusters on. And that's the space analogy. Okay? That cool? So that's the analogy. Space station. Yeah, see, that's my analogy. Mission control, space station. Control, what should I do? Here's the instruction. It looks up in some table, control, okay, you'll see, what's there? Okay, you're an add, you're a sub, okay. Turn that line high, become a sub. Basically, it looks up at a table and does that. So we're gonna talk about how to build control in 2 lectures, but that's how it does it. Pretty cool. Control and data path are 2 abstractions we created. We created these abstractions. The wiring, and then who do you control the wiring, which is so useful to think about how control logic passes that. And here's all the R-type instructions. So it's useful to have all 32 bits because now I can read from func 3, I can read from func 7. By the way, if you don't ever know why we called them there, because it's 7 bits wide. It's kind of nice to that. It's a 7-bit wide field, it's a 3-bit wide field. Func 3 is 3-bit wide. So we do use that to determine what's the operation we're sending to ALU. And rather than having 1 bit, we'll have ALU select, which is the overall general operation it does. Now we can handle all of them. There's some number of bits wide that this tells how to handle add and sub and XOR and and OR and SLT and da-da-da. All those bits get passed into that magically by some control that looks up a table and tells you what bit pattern to tell it, the ALU to do it that day. Okay? Let's do the immediates now. All right, let's go. 5 minutes left. What's different? I still read from RS1. That's the same. I still write to RD. That's the same. What's different is I got this immediate. So the first thing I got to think about is how do I take that immediate and then somehow merge it into the adder? The adder only has 2 inputs, which are right now directly fed from the register file. What do I have to modify? I got to modify the lower one. If I'm not reading from RS2, reg of RS2, I'm reading from this immediate. That has to get sign extended also. So let's talk about it. This is what we had so far. I now somehow have to get this immediate into this. So I have to take that line that used to be wired directly from the register file, from data R1, R2, that is. I have to somehow get 2 guys that can drive the same B input on that ALU. How do you have a 2-to-1? If I only knew about a 2-to-1 device that we could just go to Fry's and get. You know what that's called? A mux. We talked about it already. So whenever you have that problem of I got 2 guys need to drive 1 line, use a mux. That's the answer to that. Who would control the mux? Control, right? So there's my mux. That's my immediate. This now says, by the way, what's really cool about this is I even label this as I. B select says who drives the B line to the ALU, rather than say, oh, it's 0 or 1 and coding. No, just call it, oh, here it calls 1. Sometimes we call I. Sometimes that's a 1. Sometimes we actually label it as an I for immediate. Take it from the immediate or take it from register. Here I'm saying 1, which means take it from the immediate. So I need a new block to take 12 bits of an immediate, of a signed immediate, and extend to the 32 bits, because I can't just have 20 bits hanging free. You can't ever do that in a signal, because it won't know what it is. So I need something called an immediate generator to take 12 bits in, 31 to 20. When it's set to I, that means, oh, it's encoded in the immediate way. That means sign extend in the clever way that we've done before, because some different sign extensions are different. Sometimes it's a 0 extension. This is an immediate sign extension. So I get the 12 bits of the instruction. Already, look, here's the 32 bits coming down from IMEM. I pass 12 of them into immediate generator. Those 12 bits, those 32 bits come out to that mux. The mux says 1. The 1 drives the B, and now I'm all good. That's it. So I only had to make 1 change. I had to figure out how to get the immediate out of the instruction, and 2, how to stuff it into the ALU's B input. That's all I had to do so far. Increment this. Pass the instruction out of IMEM. The immediate goes into IMGen, immediate generator, IMGen. Those 32 bits are now sitting waiting in the mux. The control, by the way, control, when this red bar comes in, control makes its call, and then it can decide what to do. Sets this to I, sets this to 1, sets this to B select, sets this to add. That's when it knows it does. As soon as this line comes in, this line coming from IMEM, then it, after some delay, some combinational logic delay, it decides what to do. We're doing great, folks. We're doing great. And then write it back at the last stage. Data, watch. Data ins 24 to 20 still feeds into the register file. Look, 24 to 20 still feeds in this. I'm not changing that wiring. That's the data path. That register file is combinational logic. It's still looking up. Oh, you wanted this 5-bit index? You wanted some data from my register file. That still spits out on R of RS2. But what is that a problem for us? That this is garbage spitting out on that? Is that a problem? No. Why? Who ignores it? The mux ignores it. The mux says, sorry, RS2, you're garbage, dude. I'm taking from the immediate today. Boop. Puts the stop up and reads from that. Is that kind of cool? Like the signal controller on a path. All right. So how do you do this? How do we sign extend? Last line. How do I sign extend? I take this bit, which is the sign bit, really, of a 2's complement. 1 was when it's negative, negative, and I smear it. I just smear it. So I literally copy those lower 11 bits get copied. That top bit just gets wired to all the other 21 guys. Here's top 20, and here's the top bit. I just smear it. So if it's a negative number, it stays negative. If it's a positive number, it all stays positive. It's pretty cool, right? Or 0. Skip this because you don't have time. And then the conclusion is a conclusion. That's it. Isn't that cool? You better celebrate something today. You better go have a coffee or a muffin or a scone. We built an actual working computer, only for 3 instructions. It's not great, but we're going to add more next lecture. So celebrate. Yay, you did it. We did it. We built a working machine. I haven't told you how to build control yet. That's super hard. And I haven't told you how to add more instructions. So next time we're going to be like bursting through adding instruction. We'll see you next time. Thanks, folks.